So you have a quiz next week. So the quiz covers up to the last lecture before reading week. So that would be the Thursday lecture before reading week for you guys. That covers up to implementing comparable, and that's it. All right. So I'll post a sample quiz later this week, probably Saturday, I'm guessing. I'll try to get it up for Friday. And then, so you'll have a chance to see what the quiz will look like. It'll be fairly similar to what you saw on the first quiz. Yeah?
So what did you say it goes up to?
The last lecture before reading week. So basically implementing comparable. So how to implement the compare to method. Okay. All right. We were talking about composition in the last lecture. So composition arises when you have a class. It's got fields whose types are references. Right? If the fields are primitive, you don't care. Right? Composition and aggregation don't apply in those cases. As soon as you have reference types those as fields, now you have some sort of association, which can be an aggregation or a composition. Things become more complicated when you have a collection as one of your fields. Right? So for example, if you have an array as one of your fields, so if you are implementing the matrix from Lab 5, right? You probably have an array as one of your collections, as a collection of your array elements, right? You now have to address the issue of whether or not your object owns its collection, and does it own the stuff in the collection, right? So with an array of primitive type, right, you're only concerned with does the object own its array. You don't care about the elements in this case because the elements are primitive and there are no ownership issues with primitive values in Java. Right? So probably later in this lecture, I'll show you what happens when you have a collection and its elements are also reference types. All right, so I'm going to implement a very simple combination lock class. So this is just a cheap combination lock that you'd have on your bike, well, on a kid's bike anyway, right, where you have some dials, and each dial is a number between 0 and 9. So I'm going to say that our combination lock, at least 3 digits. So it could have more, right? But it has to have at least 3 digits between 0 and 9. And your lock is either locked or unlocked, right? So when you go to implement this thing, you have to decide what fields do I need, right? You look and you see, well, there's at least 3 digits. There could be more. So right away, you know that there's a collection of some kind to hold the digits, right? Then you need to know, is the lock locked or unlocked? So you need some sort of field to represent that. So a Boolean is appropriate there. Right? True if the lock is locked, false if it's unlocked. I forgot to fix the slide. I don't know why this implements comparable. That doesn't make any sense. But just ignore that. All right, so we're going to have a field here, our combination for this lock. Right? I'm going to store it in an array of int. And I've got my Boolean variable here is locked. Okay, now remember when you're working with arrays, right? I've got a field here, right? Its type is an array, but there's no actual array yet, right? And this is different than what happens in C, right? If you make an array, if you make an array int combination square bracket some number, right? You get an array of that length right away. That doesn't happen in Java, right? So you have a variable here that can hold an array or hold a reference to an array, but you don't have the array yet, right? So you have to keep that in mind when you're working in Java. Right? So your constructor has to make that array. So our no-argument constructor initializes the lock so that it is locked and it has the combination 999. So the first thing you do is you make your array, right? And it has length 3 in this case, so we have an array of length 3. Then we go ahead and set the combination to 999, and then we set the lock to be locked. Right? So that's easy. If you have a constructor that lets the caller specify the combination and they're passing in an array, right, you have to make sure that you copy that array, right? So if you're taking in an array that represents the combination of your lock, right, then you have to do what we looked at in the previous lecture, right? The first thing you do, copy the incoming object. So we have to copy that combination. In Java, the easiest way to copy a one-dimensional array is arrays copy of. Right? So that copies that array and makes the new array have that length. Right? So a copy of will let you make a shorter copy of an array or a longer copy. If it's shorter, it just ignores all of the digits, all the values after that length. And if it's longer, everything else gets set to 0 or false. Okay, so once you've got your copy, you can go ahead and validate your copy. Right, so here I'm only validating the length. You really should validate the digits that are in the array, but I'm not going to do it here because it doesn't fit on the slide. Right, so validate the copy, and now go ahead and set your combination to be equal to the new array. Right? You can't make it be equal. You can't write this combination equals combination, right? Because what ends up happening is whoever passed in the combination, whoever passed in that array, if they change their array, the combination of the lock now changes too. If you have a copy constructor, then you have to do something similar, right? So with a copy constructor, if I want to copy another combination, I have to copy the array from the other lock, right? So you could write this dot combination equals new array, blah, 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 and then copy the array, right? You could write this combination equals array's copy of other combination, blah, 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 blah. Right? Or you can just chain to the other constructor, which is what I'm doing here. Right? So this chains to the previous constructor, right? And now this constructor runs, copies the combination, validates the combination, and then sets the array to be equal to the copy. Right? So that second constructor does all the work for us. What it doesn't do, though, is it doesn't copy the state of the other lock. So you have to remember to do that as well. Right? So the documentation says it also copies the lock state. So we have to make sure that we copy the lock state as well. OK, now, whenever we talk about composition, students who have never done it before, they suddenly start making copies all over the place. It doesn't matter if you need it or not. They copy everything. Right? And it's wasteful to copy everything. Right? Not every method needs to perform a defensive copy. Right? So suppose you implement a method where somebody passes in a combination and they want to use that combination to unlock your lock. Right? So they're going to pass in an array containing some combination. Right? And you're going to check, is that array equal to the combination of your lock? Right? You don't have to copy the incoming combination. Right? You don't have to copy your existing combination. All you're doing is you're comparing two things to see if they're equal. So there's no danger of a privacy leak here. Right? So unlock looks just like this. Right? So if someone passes in a combination, you just want to know, is your combination equal to the passed in combination? Right? For arrays, you can test one-dimensional arrays for equality using arrays.equals. Right? So if the two combinations are equal, unlock the lock. Otherwise, do nothing. And away you go. Right? But you don't have to make a copy here. Right? Arrays equals doesn't make a copy. I'm not going to make a copy. There's no need to make a copy. Right? There's no danger of a privacy leak in this situation. All right, so that's what happens if you have just a plain old array of primitive types. Right? You treat it as though it were just a regular object. Right? There's nothing special that you have to do. Where things become somewhat more complicated is when you have a collection as a field, and that collection, its elements are of reference type. Right? And so this happens quite a lot because it's many classes that you implement represent or have a collection of some kind inside of them. Right? So for example, a university has a collection of faculties. Right? Every faculty has a collection of departments and schools, and so on and so on and so on. Right? A receipt has a collection of items that were purchased. Your contact list on your phone has a list of contacts. Right? From the note, ignore that. You might have a student class that where every student has a collection of GPAs and courses. And if you play video games, right, almost certain, well, three-dimensional video games anyway, those games will often have, the objects in those games will be made up of polygonal models. Right? And so a polygonal model is normally a collection of triangles in most video games. More generally, they don't have to be triangles, but triangles are easier to work with. All right, so as soon as you have a collection, you have to ask the question, what exactly is inside the collection? Right? So if I have a collection of, say, dates, right, are there date objects in the collection? It turns out the answer is no, there are not. Right? So a collection holds references to objects. Right? It does not hold the objects themselves. Right? So everything in Java is everything that involves references in Java generally means everything else is a reference. Right? So if you have a list variable, that's a reference to a list. Right? That list object inside of it has references to its elements. Right? It doesn't. The list object itself does not hold the elements. So if I make an array, a list of dates, right, and I make some dates and add them to the list, right, what ends up happening is the following. Right? So there's my array list. Whoa, sorry. Right, there's my array list. Right? Date 1, date 2, date 3. Those are 3 date objects somewhere in memory. Right? So I'm here saying 500, 600, and 700, but there's 3 date objects somewhere. Right? Those date objects are not in the list. Right? What the list is holding is a reference to the first date, a reference to the second date, and a reference to the third date. Right? Okay, so if I make a list of points, and I create a point 0, 0, and add that to the list, right? I'm then going to change my point, so its x-coordinate becomes 10, so it's now 10, 0. Right? If I print out the point, it had better print out the point 10, 0. Right? Now the question is what happens if I also print out the first point in the list? Right? So if I ask the list for its first point using get, right? Is that point 0, 0, or is that the point 10, 0? It turns out it's the point 10, 0. So you actually get D in this case. Right? Why do you get 10, 0? Because when you add P to that list, right, you add a reference to the point. So if you change P, right, then as far as the list is concerned, right, the first point in the list also changes, right, because it's also the point P, or also refers to the point P. Oh, so what does that mean? That means if you have a list of something, it's an aggregation of something. It's not a composition. Right? So a list is an aggregation of elements. It is not a composition of elements. Right? The list doesn't own the elements that it has. Okay, so there's a hypothetical student class. So every student has a collection of GPAs. Every student has a collection of courses. And every student has some sort of ID, probably a student number of some kind. Right? Notice here that this is aggregation. Right? Now, when you have a collection of stuff, when you draw the UML diagram, you don't draw the collection, right? So here, notice that it's a collection of GPAs, so it's probably a list of GPAs, right? Notice what's over here is normally not a list, right? Normally, the way you draw this is you draw the element, and then you say that there's 0 or more, right? And so the collection here is implied, and it's not completely specified in this example. Depending on the situation, you might actually draw the list, right? So if you really need to show the details of your class and you want to show the fact that it's a list, you would draw the list instead. Right? But here, I'm just drawing this as a collection of stuff, right? So 0 or more, and similarly with the courses. Right? Okay, what about a polygonal model? So a polygonal model is just a collection of triangles, right? So 0 or more triangles. Each triangle is just a collection of 3 points. Right? And so here I'm using aggregation on both of these two objects. Right? So a polygonal model is an aggregation of triangles. Triangle is an aggregation of points. Right? I'm using point 3 here. That's just the analog to point 2, right? So a 3-dimensional point. Okay, if you played any 3-dimensional video game, then almost certainly everything in that world is made up of triangles. They might be made out of quadrilaterals, but it's probably triangles, right? And so that picture there, whoops, sorry, right? If you look at its underlying representation, everything's just triangles, right? The fact that stuff looks round and relatively smooth, it's sort of coarse in this picture, but everything looks relatively smoothly shaded. It's all an illusion, right? This is all an illusion that's provided by the way that the triangles are shaded in the image. Computer graphics is all about illusion, right? Nothing's real in computer graphics. If you take the 4th year computer graphics course, you'll learn that very quickly. Okay, so what does our polygonal model class look like? So we're going to start by implementing an aggregation of triangles. So to hold the triangles, I'm going to use a list. You could use something else, right? You could use an array. Here I'm going to use a list. What does the constructor do? Well, it initializes the list, right? That's what the constructor always does. So it initializes the model to have no triangles. I have a clear method. So clear just removes all the triangles. And that's easy to do. You just ask the list to clear itself, and the list will empty itself of all of its triangles. Right? We got a size method. So the size just returns the number of triangles in the list. Right? And that's all we need for the purposes of this lecture. Okay, now, when you have a collection as a field, you need to decide on the ownership issues involved. Right? So does X own, or does it share its collection? Right? If X owns the collection, does it also own the objects that are inside the collection? Right? So those are the two questions that you need to ask. So we'll start out with the easiest one. So X is going to share its collection, and it's going to, so if it shares its collection, then it also does not own the elements in the collection. It can't, right, because it's sharing the collection. Okay, so if you're going to do this, then you're basically implementing an aggregation, which is what we're doing now. Right? So your copy constructor in this case doesn't actually need to make, if it copies another polygonal object, it doesn't need to make a new list. Right? You're going to share the list, so you're just going to share the list with the other polygonal model. Right? And so our copy constructor is very easy to implement. Right? We just write this try equals other try, and away you go. Right? So this is basically the same thing that you would do if you had primitive fields. Right? We have a method called getTriangles that lets somebody get the list of triangles. And so in this case, we can just return this.try. Right? So in this case, there's no composition involved. If composition is not involved, there's probably no copying of objects involved. Right? So what are we saying here? We're saying that the list of triangles for this object is the same list as for the other object. Right? If somebody asks for the list of triangles, we're just going to hand out a reference to our internal list. Right? If somebody changes that list, then the model is also going to change. Right? And so the picture that you get is the following. Where is this? Where's the P? Oh, here. Okay. So I've got an existing polygonal model P1. I'm going to use the copy constructor and make a new polygonal model P2. Right? So there's P1. There's P2. Right? What's inside the first polygonal model? Well, there's a list. Right? Where does the list live? Well, it's over here. Right? This list happens to have two triangles in it. Right? And so the triangles are there and there. Right? So that's P1. P2 is basically exactly the same as P1, right? It has a list of triangles, but its list of triangles is the same, right, as the list of triangles as the other model. So in fact, it's that list right there. Right? And that also means that its triangles are also the same triangles right there. Okay, so suppose we run that copy constructor. Right? Our first model, P1, has 100 triangles in it. Right? So there's P1, right? So we make a copy of it, right? So P2 also has a list that has 100 triangles in it. Right? Now we're going to clear P2's list of triangles. Right? So what's the size of P2? Well, it better be 0. Right? Now the question is what is the size of P1? Right? And it turns out in this case it's also 0. Right? So the answer is right there. Right? Because P2's list is the exact same list as P1's list. Right? They're the same list. So if you clear P2's list, you end up clearing P1's list as well. Right? Which is, again, there's nothing wrong with this happening. Right? If you've chosen to use aggregation and you've documented the fact that that's what you've done, then this is exactly what you should expect to happen. Right? So that's straightforward aggregation. All right, now this next example is still aggregation, but it's slightly more complicated. So if X decides it wants to own its collection, right, but not the objects in the collection, right, and then what do you have to do? So now you always have to make a copy of the collection, but you're not going to make a copy of all of the elements inside the collection. Right? So this is what's called a shallow copy. Right? So a shallow copy of a collection occurs. Right? when you make a new collection, right, but the elements inside that new collection are the same elements that are in the copied collection. Right? So you copy the collection, but you don't make separate copies of the individual elements. Right? And so what does that mean? It means that the references the collection is holding are aliases to references in the other collection. Right? In other words, they're just the same elements that are in the other collection. Right? And by same, I don't mean equals. I mean they're the same elements. Right? They refer to the same elements. Right? And so, yeah.
Does this mean it's a reference to a reference?
What's a reference to a reference?
Like a reference address to another collection of reference addresses to something.
Yeah, so you'll have two lists, right? But inside the two lists, the references inside those lists are all equal. They're all the same, right? But the two lists have separate addresses. So you have two list references, but you have the same number of element references still. Okay, now this is still aggregation as far as the model and the triangles are concerned, right? So still aggregation. Why is it aggregation and not composition, right? Because we're only interested in the relationship between the triangles and the model. We're not interested here in the relationship between the collection and the model, right? If you're interested in the relationship between the collection and the model, this is now composition, right? So the polygonal model is a composition of a list, but it's still an aggregation of the triangles because the model itself does not own the triangles, right? It's still going to share the triangles with somebody else, or still potentially can share the triangles with somebody else. Right? So that's a subtle but important distinction. Okay, so if you want to make a shallow copy of something, right? So if you have a list or a set, right? If you want to make a shallow copy, then the hard way to do it is as follows, right? So scopy is going to be my shallow copy. Right? So you make a new list. That's good. You've got a new list, right? Now you iterate over the original list, and you add the elements from the original list into the copy, right? And so there. That just produces, there you're simply copying the references from one list into the other list, right? And so here you've written one statement to create the list, and then you've written the loop. You don't have to do that, right? If you want to make a shallow copy, just call the copy constructor, right? So the list and the set copy constructors, they make shallow copies, right? So you get a new list. But the copy constructor runs and it does the loop for you, right? Copies all the elements from the other collection into your new collection. Right? So both list, set, and map, if you copy a map, they all perform shallow copies. Okay, so if you want to change the implementation of your class so that it now owns its collection, right? You now have to make a new list inside the copy constructor, right? So I can't write this try equals other try anymore. I now have to make a new list and make a shallow copy of that list. Right? So it's not considerably harder, but now you have to remember to make the copy, right? And the confusing part here is that now you're making a copy so it looks like composition, right? But you have to remember this is still, the model is still an aggregation of triangles, right? It's a composition of a list, but it's an aggregation of its triangles, right? So it owns its lists, does not own its triangles, right? And so the picture that this looks like now changes subtly, right? So again, we have P1 and P2, right? So there's polygonal model 1, polygonal model 2, right? P1 has its own list over here, right? That list has a reference to two triangles, right? There and there. In our modified copy constructor, when we copy P1 to get P2, right, we now make a new list, right? So that list, this list is independent of this list now, right? However, when you look at the stuff that's inside the list, it's the exact same stuff that's inside the other list, right? So in other words, it's still holding references to the exact same two triangles that the other model has, right? And that's why, right, that model is an aggregation of these two triangles, and that model is an aggregation of those two triangles, right? Neither model actually owns those two triangles. Right? They own their own lists, right? But they don't own the triangles that are in the list. Right? Okay, so we're going to run that second copy constructor now. P1 has 100 triangles in it. Right? So I make a copy, P2, of P1. Right? I'm going to clear P2. Right? And then I'm going to print its size, the size of P2. All right, so I've just cleared it, so its size has better be 0. Right? But what is the size of P1? Well, now the size of P1 remains 100. Right? Because P1 has its own list. Right? When P2 clears its list, that does not cause P1's list to also clear. Right? All right, so this one's a slightly different example now. So same copy constructor, right? So I'm going to make a copy of P1. P1 has 100 triangles in it. Right? I'm going to get the first triangle from P1, right? And I'm going to get the first triangle from P2. And I'm going to ask, are they the same triangle? Right? Not equal, are they the same? Right? And the answer is yes, they are the same triangle. Right? They are in fact the same triangle. Right? You just go back and look at the picture here. Right? What's the first triangle in this list? Well, it's the one at address 1000. What's the first triangle in this list? Well, it's the one at address 1000. Right? Same triangle. Okay, so now, what happens if X owns its collection and it also owns the elements inside the collection? Right? Now you have a composition of stuff. Right? Now you have a composition of elements. Right? So if X owns its collection and it owns the elements in the collection, now you have to perform what's called a deep copy. Right? Not surprisingly, all right, a deep copy is you make a new copy of the collection and you copy all the elements that are inside the collection. Right? So the references in your new collection, right, they are now references to new objects. Right? The objects, however, they're equal to the objects in the other collection, in the copy collection. Right? So they're equal, but they're not the same. Right? So they're not the same objects, all unique elements, right? But each pair of elements are equal with respect to the other collection. So now we really do have a composition of triangles, right? Notice that though the triangles are still aggregations of points, right? So the model here never does own the points that are in the triangles, right? It can own the triangles, but it never owns the points. Right? You can ask the question of what happens if you want to own the points too, right? And so now it becomes much harder, but we'll ignore that for now. Okay, so how do you perform a deep copy of a list? Right? So the answer is you can't always perform a deep copy. Right? And so the reason is, so you can always make a new list. Right? So I can always make a new list. That's not a problem. The problem is you may not be able to make a copy of the elements inside the list. Right? So here I'm going to iterate over the list that I want to copy. Right? And I want to make a copy of each one of these elements D. Right? Now for the date class, we know how to do that. Right? We know that we can do dGetTime and then pass that to the date constructor. Right? It's possible that you end up in a situation where the elements that you want to copy, there is no copy constructor and there is no obvious way to make a copy of the elements. Right? So it is possible for that to happen. So in general, you can't always make a deep copy in Java. Right? But if you can, it looks something like this. Right? You're going to iterate over the collection that you're copying. You're going to copy each element and add it to the new collection. Right. Okay, so if you're going to modify our polygonal model constructor so that the polygonal model is now a composition of triangles, you have to make a deep copy of the list. Right. So make a new array list. Right. So there's our new list. And now write a loop, right, where you loop over the other triangles. Right? For each triangle, you make a copy of that triangle and you add it to your new collection. Right? So copy both the list and the elements inside the list. Right? And now the picture looks like this. It actually spans another slide. Right? So there's P1, there's P2. Right? Copy constructor runs, so P2 gets created. right? And we make a copy of that list, right? So we make a deep copy of this list. So we make a new list. So there's our new list, right? Now when we make the new list, we iterate over the triangles in the original list, and we make a new copy of each one of those triangles, right? So inside our new list, there's a new triangle, right? So that 2,000 is different from that 1,000. That 2,100 is different from that 1,100 that's there, right? But that triangle here, the one at address 1,000, is equal to the triangle at address 2,000, right? Similarly, the triangle at address 1,100 is equal to the triangle at address 2,100, right? They're different triangles, so there are your other two triangles, right? So they're different triangles, but they are equal, right? So that one is equal to that one, right? And that one is equal to that one right there. All right. Polygonal model P1 has 100 triangles in it, right? We make a copy using our third copy constructor. We clear out P2, right? What's the size of P2? Well, it's 0. What's the size of P1? Well, P1's list doesn't change, right? Because P1 has its own list. So it's still 100. All right, same thing. So P1 has 100 triangles in it. P2 is a copy of P1. If we ask P1 for its first triangle and we ask P2 for its first triangle, right? And we ask, are those two triangles the same triangle? Right? You get back false. Right? They're no longer the same triangle because we made new triangles for the second model. Are they equal? Well, yes, they're equal, right? Because we copied each triangle from the first list into the second list. Boom. All right, so that's what happens when you've got composition with a collection, right? So you can keep on going, so that's the problem, right? If your elements can also be collections of stuff, right? So that here, a triangle is a collection of points, right? If you want the case to be that the model owns the points that are inside each triangle, right? You now have to go down one more level, right? So each time you copy the triangles, right? It's not sufficient just to run the copy constructor for a triangle because triangle says it's an aggregation of points. You now have to go into the triangle class, figure out how to get the 3 points out of the triangle and make a new triangle, right, using new points, right? And so now you have to copy all the points belonging to all the triangles, right? And it can keep on going, right? If that thing is an aggregation or a composition of something else, you now have to copy the something else as well, and so on and so on and so on and so on, right? And so in general, it's very hard to make a complete deep copy of an object because you never know how far you have to go until you can stop copying stuff. All right, any questions on, yes?
So would just like the 2 layers be considered a deep copy even if there's more like aggregations?
So the answer is yes. However, it kind of depends on the context of the problem, right? If you happen to know that this thing here, well, actually we do know that this thing here is another collection of something, right? Some people argue that to deep copy it, you have to go all the way down to the bottom until you've copied everything. I think, though, in this case, it's accurate to say that this is a deep copy of the triangles. Yeah. Any other questions? Okay, so we've looked at 4 relationships between classes, right? Dependency, association, aggregation, composition, right? There's one more important one. And the important one is inheritance. But before we get there, we're going to make a slight detour. Well, it's sort of related. So before we actually talk about inheritance, I'm going to talk about interfaces. Interfaces are close to inheritance. They're not quite the same thing, but it's close. Right? So remember what an interface is? So we saw an interface, we've seen the comparable interface in the class so far. Right? We've seen some other interfaces too. We've implemented comparable though. Right? So remember what an interface is. Right? So it's a specification of the methods that a class must provide, right? Not an implementation of the methods, right? It's something that says your class must have these methods must do this particular thing, right? Most interfaces are usually made up of one or more method declarations, and there's no implementation. Right? Newer versions of Java allow you to implement some of the methods in an interface. So I'll show you how that looks I don't know if it's today or in another lecture. All right, now remember what an interface is. So things like list or a set or a map, those are all interfaces, right? They're actually types in Java. So you can make a variable whose type is list string, right? And you can put anything that implements the list interface in that variable, right? So I can make an array list, and I can store an array list in a list variable. Right? I can make a Java util linked list and store that in a list variable. I can have my own list class and store that in a list variable as long as my list implements the list interface. Right? So interfaces are in fact types. Right? So notice here, the type on the right-hand side is not the same as the type on the left-hand side. Right? And so here, this is an example of what's called substitutability in Java. Right? It's possible to substitute one type for another type. Right? And that's what inheritance is all about. Right? So inheritance is about creating a hierarchy of types where you can substitute types that are lower for types that are higher in the hierarchy. Okay, so a class that implements an interface has to provide all the methods that are declared in the interface. So if you want to implement comparable, you provide compare2 in your class. Right? There's an important interface in Java called iterator. So the iterator interface is, an iterator is an object that knows how to iterate over a collection of elements, right? Or a sequence of values. Right? So when you write a for each loop over a list, you're actually using an iterator. Right? It doesn't look like you're using one, right? But the language actually the compiler makes an iterator for you, and then it uses the iterator to loop over the elements of the list or set. Right? So the language actually hides all of that from you, because you really don't need to know the details of all this, right? You just want to loop over the elements. So it hides all of that for you, but in fact, that's what's happening. Okay, so what does the iterator interface look like? Well, it's an interface, right? Its name is iterator. It's a generic type, right? So that type T, that's the element type of your list, right? So if you have a list of string and you create an iterator, then you have an iterator of string. Right? If you had a set of, I don't know, if you had a set of dates and you loop over the set using a for each loop, then it's using an iterator over dates. Right? The iterator has two methods. So it has next and it has next. Right? So has next is true if there are still some elements to visit in the iteration. Right? Next returns the next element in the iteration. So any object that implements iterable can be a target for a for each loop, right? So that means if you have a class that has a collection of stuff and your class implements the iterable interface, someone can write a for each loop that loops over the elements of your class. Right? So in a list, you can write a for each loop on a list, so it implements iterable. Right? Sets also implement iterable. Oddly enough, arrays, which you can also write a for each loop over, right? Arrays do not actually implement the iterable interface. The language only pretends that they do, right? So in other words, the compiler does some magic for you to loop over the elements of an array, right? But it doesn't actually use an iterator in that case. Okay, so notice that there's there's another interface here, right? So the interface here is called iterable. Right? Iterable has one method. It's called iterator, right? And it provides an iterator, right? So that's all it does. All right, so in Python, so people who have used Python, who have used exclusively Python, really like Python loops, right? Because to write a counting style loop in Python, you just write for I in range and something like that. Right? So for I in range 0 to 10 gives you a loop that counts from 0 to 9. right? And so Python programs like that because they don't like the C-style for the C-style counting loop, right? That's much easier to write, right? So in Python, there's only one type of loop. It looks like this, right? There's only one type of for loop. It's for something in, right? So everything in Python iterates over a sequence. Now, you can't do that in Java, right? So in Java, if you want a counting style loop, you have to write a C-style loop to do that. But if you wanted to, you could emulate the Python style loop by making your own class called range or something else, right? So here we can do the exact same thing. We just have to implement a range class that knows how to count from 0 up to but not including 10, right? How do you do that? Well, you make a class called range, right? And now range implements the iterable interface, right? The problem is when you implement iterable, you also have to provide an iterator. So now we have to also implement an iterator class to do this. All right, so let's see what this looks like. All right, so I'm going to implement the class called range. Now remember, range is just going to count from 0 to some integer, to some number, right? I want to use it like that, right? So I have to implement iterable, right? The numbers that the range produces are integers, so it's iterable integer, right? And now I need something that can count from some starting value to some end value, right? So for example, here we can say range 5, 10, and it'll count from 5, 6, 7, 8, 9. Right? So we're not always counting from 0. So there's a starting value and there's a stopping value, right? Because I need to know, basically this thing needs to know where is it counting from and where is it in the range, right? That's what it, well, all right. So the range needs to know what is the range of values. The iterator needs to know where is it in the range of values. Right? If we provide we can provide a constructor where you just pass in the stopping value, right? So that counts from 0 up to but not including the stop value, right? And our general constructor here takes in both the starting and the stopping value, right? It has some validation here, right? So if the stopping value is less than the start value, we're going to throw an exception. So this one only counts up. You can arrange it so it also counts down, but for our purposes, we're only going to go up. Right, and we'll set this stop and this start and stop equal to start and stop. Okay, and now the only method inside of our class is the method that iterable specifies. Right? So remember, we're implementing iterable. So iterable says you must provide an iterator method. Right? And the iterator must return an iterator over integer values. Right? And so now we need to provide our own iterator class, which I'm going to call range iterator. Right? So we have to implement this iterator class now, and we have to put it somewhere. So in this case, it turns out the appropriate place to put it is inside the range class itself. Right? And so this is the first example of when you've seen what's called a nested inner class in Java. Right? So a class that's defined inside of another class is called a nested class in Java. Right. This particular one is special. It's also an inner class, but we'll get to that in a second. Right. Now, why is it private? So you normally can't make a private class. Right. So normally, if you make a top-level class, it can only be public, public or package private. Right. It can't be anything else. If you make an inner class, though, you are allowed to make it private as well. Right. By making the inner class private, that prevents anybody else from trying to use that class directly, right? So essentially what we're doing here is that we're creating a class whose only purpose is to serve the class that it's in, right? So in other words, range iterator is only important to the range class, right? No one else needs to know that it exists, right? Anybody who wants an iterator over a range just calls the iterator method, right? But no one ever needs to make their own range iterator object. Right? So we can make it private. Right? And so when you do something like this, you're saying that the class that you're creating is an implementation detail of the class that you're providing. Right? So range iterator is just some implementation detail that no one else needs to know about, but range needs it in order for range to work. Right? And so the consequence of this is that only the range class itself can actually make a range iterator object. And it does that right there. Right? Okay, so this is just so now that it's a class, it's just range iterator is just a class. So the way you implement it is the same as any other class. It just happens to be inside of another class. Right? Now our iterator is going to implement the iterator interface. Okay, so a nested class is a class that's defined inside of another class. Right? Usually when you do this, but not always, right? Usually when you do this, the nested class exists only to serve the class that it is defined in. Right? If that's not the case, so in other words, if someone else would find that inner class to be useful, sorry, the nested class to be useful, then it probably shouldn't be a nested class. Right? It should probably be its own separate top-level class. The standard library actually breaks that rule. Right? So if you look at the entry class that's inside a map, that is a useful class, but it's defined inside the map interface. So there is a counterexample there. Right? When you're implementing an iterator, it's almost always defined as a nested class. Right? Why? Because you can't have an iterator without its enclosing class anyway. Right? It doesn't make sense to have a range iterator if you don't have a range. The only place it makes sense to put this class is inside the range class itself. Right? So it's the same with list, right? So if you ask a list for an iterator, internally there's some class that you can't see, right? So there's a list iterator class. And you don't actually know that it exists unless you actually look at the source code for list, right? So it doesn't make sense to have an iterator over a list if you don't have a list to iterate over, right? And it doesn't make sense to have a range iterator if there's no range to iterate over. Right? So the nested class is in fact the best choice in this case. Okay, I'm going to do this slide and then we'll call it quits. You'll notice that here I said that this is a nested inner class. Right? So a nested class is an inner class if that class is not marked as being static. Right, so let's go back here. Right, so this is just private, blah, 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 blah. Right, the keyword static doesn't appear anywhere here. Right, so you can mark a nested class as being static, and then it means something else, which I'll tell you about in a couple of weeks. Right. Okay, so objects of an inner class. Right, so in other words, a range iterator. Right, inside of every range iterator, there's a reference to the range that created it. Right, you can't see that reference. You can't easily see that reference directly, right? But it's there. So every range iterator object has a reference to its range object, which kind of makes sense, right? The iterator needs to know what range is it iterating over. So it needs a reference to that range. Right? If you have an inner class, right, then that class is allowed to access the fields of the enclosing class. Right? And so that means range iterator gets to see everything that's inside of its range object. Right? So what does that mean? It means inside range iterator, right, I'm allowed to access the fields start and stop, even though they belong to range and even though they're private. Right? So even though they're private, range iterator has access to those two fields here. The way it gets access to them is weird, but it does have access to them. All right, so we'll call it quits right there, and then we'll finish off the implementation in the next class. If you're in the lab next, Matthew has your quizzes, so he'll have them back to you in the lab.